Welcome to tutorial number 8. You're watching the Fast Track Multimedia Standard course brought to you by the Radio and Electronics School. These materials are copyright to the Radio and Electronics School and Ron Bertrand. In this tutorial we're going to be talking about capacitors and capacitance. Capacitors are the device, the object, and capacitance is the property that capacitors have. Firstly, let's talk about the construction of a capacitor. Before we talk about what a capacitor does, how is it made? A capacitor consists of two conductive plates. Each plate has got an area, and each plate is separated by an insulator. The capacitance of a capacitor is dependent upon the area of these two plates and the type of insulator used between them. In this drawing, the insulator is air. We will learn later that many different types of insulators can be used in capacitors. When an insulator is used between the plates of a capacitor, it is called a dielectric. So a capacitor then is simply two plates, two conductive plates, separated by a dielectric by a distance d. The capacitance is dependent upon the area of the plates and the distance between the plates and the type of dielectric. If the area of the plates is increased, the capacitance increases. If the distance between the plates decreases, then the capacitance increases. The dielectric also determines the amount of capacitance, and different dielectrics for a different distance will give us different capacitances. Air has what is known as a dielectric constant or permittivity of 1. Permittivity or dielectric constant is the ability of a material to concentrate electric lines of force. Because a capacitor is going to have a voltage placed across it, between the plates there will be an electric field. If the dielectric is capable of concentrating that electric field, the capacitance will be higher. In this capacitor we're using air as a dielectric. It has a dielectric constant or permittivity of 1. If we were to use something other than air, suppose we used a material with a dielectric constant or permittivity of 10 in this capacitor, as opposed to 1 of air, then the capacitance of this capacitor would increase by 10 times. So capacitance is directly proportional to the area of the plates. That means if we double the area of the plates, the capacitance doubles. And capacitance is inversely proportional to the distance between the plates. So if we halve the distance between the plates, we double the capacitance. Capacitance is also directly proportional to the permittivity of the type of dielectric we use. If we use air, dielectric of 1. If we replace that with a permittivity of 5, with a material with a permittivity of 5 rather than air, then the capacitance would increase by a factor of 5. So capacitance is directly proportional to the area of the plates, directly proportional to the permittivity of the material between the plates, and inversely proportional to the distance between the plates. Here is another diagram of a capacitor, the construction of a capacitor. It doesn't really show you how it's physically made. I'll show you that in a moment. But just to reinforce, every capacitor has two conductive plates, normally made of metal. Aluminium is a common material used for capacitors, so each plate would be a conductive material such as aluminium, and the dielectric is the insulating material between the plates. It could be air, could be mica, could be polyester, could be ceramic. They're common dielectrics used in capacitors. This diagram shows you exactly how a capacitor is made in practice. We have two conductors. They're normally very thin, something like aluminium foil. Two conductors separated by an insulator, and a wire is connected to each conductor. And then the whole lot is rolled up into a roll with two wires coming out of the capacitor. That roll then is now going to be much smaller than the capacitor, the flat capacitor, and that can be packaged into a can and labelled with two wires coming out as a capacitor. And here we have some examples of capacitors. Now remember, they're rolled up. You saw the diagram earlier. The dielectric and the two plates are flexible, and they're rolled up into a cylinder and packaged as they are shown here. This is an electrolytic capacitor. You may be able to work out there that it says 4 microfarads, 500 volts DC. Capacitors are given two ratings. They're given their capacitance, in this case 40 microfarad, at least it looks like 40 microfarad to me, and this capacitor can withstand 500 volts DC. Capacitors have to be given a voltage rating as well as a capacitance rating, because the dielectric can only withstand so much electrical pressure, so much voltage. If we were to put more than 500 volts DC onto this 40 microfarad capacitor, the dielectric would break down and conduct, and the capacitor would explode. This is an electrolytic capacitor, and they've got a chemical paste inside them, and that chemical paste is used to create the dielectric during manufacture. The dielectric is created during manufacture, and should those capacitors be reversed polarized, that is, if you put the wrong voltage on the positive lead and the negative lead, they will explode. Also, if you put the voltage the right way around but you exceed this 500 volts DC, the capacitor will explode. And particularly when they're reverse connected, they can explode and make quite a bit of mess, because all that paste I spoke about for an electrolytic capacitor would end up all over the radio. So notice how there's a positive sign here, so that indicates that this is the positive lead, then this is the negative lead. That's a polarized or electrolytic capacitor. This is also an electrolytic capacitor, as is the black one on the left. The others are not polarized capacitors. This is probably a polyester capacitor. This is a ceramic capacitor. They are not polarized. These ones can be connected to positive and negative either way around. This capacitor is polarized. It's an electrolytic capacitor. Likewise, this is a polarized capacitor. It must be connected with positive to positive, negative to negative, otherwise you will destroy the capacitance and probably do some damage to your radio. And I've seen them explode with such force that the can that the capacitor's in could fly across the room like a 22 bullet. I did this once in a practical demonstration in a classroom, and I deliberately reverse polarized a capacitor like this, and it exploded, and the aluminium can flew across all the students' head and left an indentation in the rear wall. Needless to say, I haven't done that again without a bit of perspex in front. But electrolytic capacitors are dangerous if you connect them the wrong way around. All of these capacitors are large electrolytic capacitors. I can just make out it looks like 450 volts. So these are polarized capacitors. There's a positive and a negative lead. There will be a positive sign on the positive terminal, and should you connect them around the wrong way, they will explode. And this capacitor looks to me like it's about 3,300 microfarad. That's a bit hard to make out, but all capacitors have a capacitance value on them, 400 volts it looks like, and it looks like 3,900 microfarads or something like that. They're electrolytic capacitors. Capacitors such as this would be most suited for use in a 12 volt power supply for an amateur transceiver. You need to know that. You need to know an application for electrolytic capacitors. Large electrolytic capacitors is a power supply, a low voltage, high current power supply. The advantage of electrolytic capacitors, the disadvantage is they're polarized, but the advantage of electrolytic capacitors is that you can get a great deal of capacitance into a relatively small package size. On the left hand side we have the symbol for a capacitor, which is a fairly logical symbol because it shows the two plates and the dielectric in the middle. The symbol doesn't tell you what type of capacitor it is, just tells you that there's a capacitor in the circuit here. If it were an electrolytic capacitor, one side of the capacitor would be marked with a positive symbol. This is the equation for determining the capacitance of a capacitor. You do not have to know this equation. However, I think you should remember it, because what you do have to know for your assessment is the factors which affect the capacitance of a capacitor. Capacitance is measured in farads. If you were to put 1 volt across a capacitor, it will charge up. If we connected a battery to this capacitor, say with negative at the top and positive at the bottom, then electrons would run into the top plate, making the top plate negative, and leave the bottom plate, making the bottom plate positive. And if it was a 10 volt battery, those electrons would keep running in to the negative plate and leaving the positive plate until the voltage on the capacitor was equal to the supply voltage, in this case 10 volts. If we remove the battery, then the capacitor remains charged with electrons on the negative plate and a deficiency of electrons on the positive plate. So a capacitor is a means of storing energy by placing a charge on its plates. The actual energy is stored in the electric field between the plates. We can do lots of things with capacitors. We can use them to filter voltage. We can use them to supply power to a part of a circuit for a short while. But unlike a battery, once a capacitor is discharged, it needs to be recharged again from a source of power. Capacitors do not make any energy themselves. They get their energy from a power source such as a battery. They get charge on their plates, and they will hold that charge on their plates, some of them for many days or even hours. Now back to the formula. The formula for capacitance, C in farads, is the permittivity multiplied by the area of the plates. If the plates are unequal area, it's the area of the smaller plate, and d is the distance between the plates. This formula is so useful because it tells you how the dielectric, and you would need to look up in an engineering handbook the permittivity of the dielectric, the area of the plates, and the distance between the plates. Now, what this is a fraction. Just like 1 over 2 is a fraction. A fraction has a top part we call the numerator, it has a divisor, and it has a bottom part called a denominator. Everything in the numerator is a direct proportion. In other words, capacitance is directly proportional to permittivity, or dielectric constant. That means if you double the dielectric constant, you double the capacitance. If you increase the dielectric constant by a factor of 10, you would increase the capacitance by a factor of 10. That's what a direct proportion is. And whenever you see equations, anything in the numerator, the upper part of the equation, is a direct proportion. Anything in the bottom part of the equation is an inverse proportion. Get to that in a moment. So capacitance is directly proportional to the permittivity of the dielectric material. Capacitance is also directly proportional to the area of the plates. If you double the area of the plates, you double the capacitance. If you halve the area of the plates, you halve the capacitance. D is in the numerator, so that's an inverse proportion. Capacitance is inversely proportional to D. If we were to double D, we would halve the capacitance, because it's an inverse proportion. It does the opposite to permittivity and area. If we wanted to increase the capacitance, we would have to decrease the distance between the plates, because this is an inverse proportion. So capacitance is directly proportional to the permittivity, or dielectric constant, two names meaning the same thing. Capacitance is directly proportional to the area of the plates. Capacitance is inversely proportional to the distance between the plates. In this schematic diagram, I've drawn a capacitor. It's an electrolytic capacitor, so it's got one side marked positive, and you'll notice that is connected to the positive side of the battery. If we reverse connected that, this capacitor would be destroyed. It's a 22,000 microfarad capacitor, and the voltage it can withstand is 16 volts DC. Put any more than 16 volts on this electrolytic capacitor and the dielectric will break down and it will explode. We've got a 9-volt battery. That's the symbol for a battery. The large wire is positive, the small wire is negative. We're connecting the battery to the capacitor through a resistor and a light emitting diode when the switch is in position A. The light emitting diode's there just to tell you, or us, that current is flowing. And the 470 ohm resistor is to limit the amount of to limit the amount of current flowing. If we put the switch in position A, electrons will flow from the negative terminal of the battery to the negative terminal of the capacitor. Electrons will leave the positive terminal of the capacitor and flow through the light emitting diode, making it light up through the resistor and back to positive. If we leave the switch in that position for a while, that capacitor will charge. If we had a voltmeter across the capacitor, and I'll show you that shortly, when the capacitor is charged, the voltage across the voltmeter would measure 9 volts, the battery voltage. When the capacitor first begins to charge, it charges quickly, because after it's first connected there may only be 1 or 2 volts, and notice that the voltage on the capacitor is positive at the top, The battery is positive at the top, so the voltage on the capacitor is opposing the battery voltage. So as the battery begins to charge the capacitor and the voltage on the capacitor gets higher and higher, approaching 9 volts, the current in the circuit decreases because the capacitor begins to push back against the 9 volt of the battery. It's a bit like blowing up a balloon. As you blow up a balloon, it becomes harder because the air pressure that you're blowing into the balloon is pushing back against the air pressure of your mouth blowing the balloon up. If the switch were switched to position B, the capacitor would remain charged because there's nothing connected to it when it's at B, and when switched to C, the capacitor would discharge through the 1 ohm resistor. Well, it would flow this way from negative at the bottom, current would flow in this direction here. If we put a light emitting diode there instead of a resistor, when we throw the switch to C, the light emitting diode would come on and glow, and as the capacitor discharged, the light emitting diode would dim and eventually go out when the capacitor was discharged. I've thrown the switch from A to B. The capacitor is now fully charged. It has 9 volts across it because it was connected to A. It charged up slowly to the 9 volts of the battery. So in position B, this capacitor has 9 volts across it. It can't discharge because there is no complete circuit. And in the final diagram, I've moved the switch from B to C. The capacitor is fully charged when it was on B. Now that I've moved it to C, the capacitor will discharge from negative at the bottom through the resistor and back to the positive plate. So all of the excess electrons on the negative plate will now flow through the circuit to the positive plate until there is eventually no voltage and no charge on the capacitor. We're discharging through a 1 ohm resistor. If we discharge through a light or a lamp, we would see the lamp come on brightly when the capacitor is fully charged, and as the capacitor discharges, we would see the lamp dim. Here we have a table of common materials and their permittivity. You don't need to remember these numbers, but you probably need to remember some of the materials we actually do use to make capacitors. But again, you don't need to remember the permittivity, you just need to know that permittivity is the ability of a material to concentrate electric lines of force, and because of that, if we put a higher permittivity material into a capacitor, it will increase its capacitance in direct proportion. Some of the interesting ones that we do use is glass. It has been used for capacitors. Mica is very common. So a mica capacitor would have a mica dielectric. Notice that mica has a relative permittivity of 5.628. So suppose we had an air capacitor and then we inserted a dielectric constant, a mica, into it with a dielectric constant of 8, then the capacitance would increase by a factor of 8 times. I think rubber is being used. I don't think it's used anymore though. Notice air changes its permittivity slightly with temperature, not much, but generally speaking we take the relative permittivity of air to be 1. All you need to remember is that the capacitance of a capacitor is directly proportional to the permittivity of the dielectric. It's also directly proportional to the area of the plates and inversely proportional to the distance between the plates. Here we've got an animation of a capacitor charging and discharging. Let me explain the circuit to you. I'll just scroll up a little bit. Okay, here we have a battery. The top of the battery is positive, the bottom of the battery is negative. Let's see where electrons can flow at the moment. Electrons can flow from the negative terminal through a resistor, through an ammeter. And notice I said ammeter and not amp meter. The meter that measures electric current is called an ammeter. So the current's flowing from negative through the 100 ohm through the ammeter, so we'll measure it, and into the negative plate of the capacitor. So electrons flow from negative to the negative plate of the capacitor. Electrons leave the positive plate and flow through a light bulb, through a switch, and back to the positive plate. At the moment we have a voltmeter across the capacitor and it's measuring 5 volts. So the capacitor is fully charged right now, and so there is no current flowing in this circuit at all. The battery is 5 volts, the capacitor is 5 volts, so you have 5 volts pushing against the battery voltage of 5 volts, so you have no current. When I operate this switch, it places a short circuit here and the capacitor will discharge. Now if you watch the voltmeter and you watch the ammeter, when I operate this switch, you'll see the discharge current through the ammeter, and you'll also see the voltage on the voltmeter dropping all the way down to 0 volts. So let's do that, and there's no resistor, so that will happen very quickly. Didn't even see the current dropping. I'll just stop that again, because as soon as I let go, the capacitor is going to charge. So we've got a short circuit on the capacitor now. It has no voltage on it. You can see there's no charge on the capacitor. The ammeter is measuring 0 amps. The voltmeter is measuring 0 volts. When I release the switch, the capacitor will begin to charge, and you'll see that on the ammeter and on the voltmeter. And on the table on the right hand side, you will see a display of the capacitor charging. Voltage is charging 2.6 volts. Can only go as high as 5 volts because that's the battery voltage. You notice the current is decreasing now because the capacitor is becoming charged, nearly at 5 volts. So we're nearly at 5 volts, and that will take a little while for it to actually reach 5 volts, but eventually it will. And the capacitor is fully charged. We'll presume it's 5 volts now because the current is 0, and in a short while that will say 5 volts. Now I can do one other thing. I can move this switch down to this position. If I move this switch down to this position, I'm disconnecting the battery, and the capacitor can now discharge from negative. It will flow through the ammeter, through the 100 ohm resistor, through the switch, across here. When I move that down, it'll flow across here. The lamp will light up and electrons will come back to the positive terminal of the battery. Again, when I throw that switch to this position, electrons will leave the negative terminal. You'll see the current on the ammeter. You'll see the voltage decreasing on the voltmeter, through the 100 ohm, up through the lamp, lighting up the lamp, and back to the positive terminal of the battery. Let's just watch that happen. There we go. Voltage is dropping, current is decreasing, lamp is on, the capacitor is discharging. And so we're able to use a capacitor to store electrical charge, and that will provide us, see the lamp is dimming, the voltage is falling, and that will supply us with electricity while there is charge on the capacitor. Charge has nearly disappeared, current is almost down to zero, the lamp has gone out, voltage is almost down to zero, our capacitor is for all intents and purposes practically discharged. If I throw the switch back to the other position, we're now charging the capacitor, and lighting the lit lamp is showing that charge current. So after a short time, the capacitor will be 5 volts. How quickly the capacitor charges depends upon the amount of capacitance and the value of this resistor here. I hope that's a useful demonstration for you. What you will need to know how to do is how to find the total capacitance of capacitors in parallel and in series. What I've drawn is 3 capacitors of 30 microfarads in parallel. Don't forget, capacitors also have a working voltage as well, so I'll give them 10 volts. So they're 3 30 microfarad capacitors, each have a voltage rating of 10 volts. What is the total capacitance? When you put capacitors in parallel, you are in effect increasing the size of the plates. If you could imagine, I'll see if I can do it for you. By doing that parallel connection, what we have in fact done is connect the capacitors together to make one very large capacitor. I know it's a bit rough, but it'll do. By connecting them in parallel, we've actually increased the size of the plates by a factor of 3, so the capacitance is greater. So we now really, by connecting them in parallel, we really only have one big capacitor. What is its capacitance? Let me just get rid of that rubbish. You simply add them up for capacitors in parallel. CT, the total capacitance, equals C1 plus C2 plus C3. So that's going to equal 30 plus 30 plus 30 equals 90 microfarads, 10 volt. The voltage rating is still going to be 10 volts because if we put 10 volts between A and B, each one of those capacitors will have 10 volts across it. And I'm assuming, well, I'd like you to assume that each one of those capacitors has a working voltage of 10 volts. So capacitors in parallel is easy. You simply add the total capacitance up to give you the total capacitance. Now I've got the same 3 capacitors, 30 microfarads, 10 volts each, and I've connected them in series rather than parallel. When things are connected in series, they're connected end to end. And just have a look and make sure that I've done that. We go from A and we go into one capacitor, and from that capacitor we go to the next one, and from the next one, and so on. The capacitors are connected in a string. I could have drawn them in a straight line, but I chose to connect them up that way, but it would be the same thing if I rotated them 90 degrees and drew them in a straight line. Now, what do you think would happen to the capacitance when we connect capacitors in series? Well, what we're doing when we connect capacitor in series, we're in effect increasing the thickness of the dielectric. The dielectric is now 3 times as thick as what it was before, and that's going to cause the total capacitance of 30 microfarad 10 volt capacitors in series to be less than 30 microfarads. The total capacitance of this circuit is less than 30 microfarads. In fact, it's a third. And a really good rule for you to remember for your assessment is that when capacitors are the same value in series, you simply divide the number of capacitors into the value of one of the capacitors. So let me type that for you. Total capacitance in series equals the value of one capacitor, and they all have to be the same value in order for you to use this equation, and in your assessment they always will be the same value if you get capacitors in series. So the value of one capacitor divided by the number of capacitors only works when they're all the same value. In this case 30 microfarad, 10 volt. Okay, so that would mean 30 microfarads divided by 3 equals 10 microfarads is the total capacitance of this circuit. However, because we've increased the thickness of the dielectric by putting capacitors in series, the voltage rating of one dielectric is 10 volts. The voltage rating of two capacitors in series is then 20 volts, and 3 is 30 volts. So putting capacitors in series decreases the capacitance but increases the voltage rating. So that circuit has a total capacitance of 10 microfarads, and it can now withstand a voltage rating of 30 volts. For your assessment, you will always be given capacitors of the same value. They'll all be 10 microfarads, 20 microfarads, 100 microfarads, whatever. So you can use the easy way that I showed you before. However, it's handy to know, just for your own sake and your hobby of amateur radio, how to find the capacitance of capacitors of different values. So I've drawn a series circuit using the conventional method, unlike I did earlier where I just linked them up, but it's still a series circuit. And now I've got 3 different value capacitors, 10 microfarad, 20 microfarad and 30 microfarad. The equation for that is there. The total capacitance is the reciprocal of the sum of the reciprocals of the individual capacitors. So you have to find the reciprocal of 10 microfarads, 20 microfarads and 30 microfarads. We don't need to use microfarads because they're all microfarads. When we're adding apples to apples, we can just drop the units from the end of it. Because they're all microfarad, we can just use 10, 20 and 30, and that's what I've done here. I've just inserted them into the equation. Then I've done it the hard way. I've gone and found out how much 10 divided into 1 is, which is the reciprocal of 10. And on your calculator is a 1 over x key, and you just type in 10 and press 1 over x, and it would divide 10 into 1. But I did it the hard way. The reciprocal of 10 is 0.1, the reciprocal of 20 is 0.05, the reciprocal of 30 is 0.0333, recurring, that's what the apostrophe means. And when we add all of them up, we get 0.1833, and when we finally do our reciprocal again, we've got to divide this answer into 1. 0.1833 divided into 1 is 4.455 microfarads. Now you don't have to remember that. Don't let it hassle you. If you can't remember that, you will not have to do it. You'll always get ones the same value. If there were 3 100 microfarad capacitors, you simply divide 3 into 100 to give you 33.3 microfarads. If I haven't mentioned, and I'm not sure that I have, you should remember that when capacitors are connected in series, the total capacitance is always lower than the smallest value of capacitance. The smallest value of capacitance in this circuit is 10 microfarads, and the total capacitance is 5.455 microfarads. It's always going to be that way. The total capacitance of capacitors in series will always be less than the lowest value of capacitance. Before we leave this, and again, you don't have to do it. I hope you don't berate me for showing you things that you don't have to know, but sometimes it just makes life a whole lot easier if you know a little bit more about something sometimes, because it's actually easier. What I'm going to do is this calculation, CT equals 1 over 10, 1 over plus 1 over 20 plus 1 over 30. In other words, the capacitance total is the reciprocal of the sum of the reciprocals. Now, I brought up my calculator. Like all calculators, I'm going to press all clear to clear the last command in case there's one just hovering about. That'll give me a faulty answer. Think about what I'm going to do. I'm going to get the reciprocal of 10 and add it to the reciprocal of 20 and add it to the reciprocal of 30, get the result, and then find the reciprocal of that answer. So 10, and the reciprocal key is 1 over x, so now I've got the reciprocal of 10, plus 20 reciprocal, plus 30 reciprocal, equals, and now we've got our 0.1833, and the last thing to do is press reciprocal, and we get 5.454545 recurring microfarads. That should be a 4. That is so useful. I know your calculator might be a little bit different, but it's so useful I'm going to show you how to do it again. If you're having trouble with math, I'd recommend you get the Radio Electronic Skills calculator, and I also recommend you get their multimedia course on how to use a calculator for amateur radio. It's not expensive, and it'll help you a great deal. All right, I am going to do this calculation on the calculator again to show you how it's done. I'm going to find the reciprocal of 10, 20 and 30 and add them up, and I'm going to find the reciprocal of that answer as well. All clear? Okay, 10 reciprocal plus 20 reciprocal plus 30 reciprocal equals, and the reciprocal of that is 5.45 microfarads. Now I think that's very easy, and that would be the method I would choose if I was going to be preparing for an amateur radio exam, using the and this same equation is used for resistors in parallel as well, and it's the same technique on the calculator. Let me just get rid of the calculator. For resistors in parallel, that would be R1, that would be R2, and that would be R3, but the technique is just the same. So for capacitors in series, resistors in parallel, and also for inductors in parallel, this same equation works. It doesn't have to be just 3, it could be 10 resistors, it doesn't matter. So if you're trying to find the total I know we haven't done inductors yet, but if you're trying to find the total inductance of 3 different value inductors, you would use that equation, and the technique on the calculator is the same. So inductors in parallel, resistors in parallel, and capacitors in series, if you know this formula, you'll be able to do any of them. And I'll just show you one more time how I did this, how I did the calculation. 10 reciprocal plus 20 reciprocal plus 30 reciprocal equals, and I think I made a mistake there. Let's do that again. 10 reciprocal plus 20, reciprocal plus 30, reciprocal equals, and the reciprocal of that. How easy is that? If you don't want to do it, don't bother. All of the values that you get in the standard amateur radio assessment, the values will all be the same. But you're going to be stuck up the creek without a paddle if you've got to find the total capacitance of capacitors, resistors or inductors one day if you don't learn how to do that calculation. To give you some idea of how a capacitor may be used, if you go to the Radio and Electronics School website, go to Supplementary on the main menu, you can download this GIF animation that I've got on the screen at the moment. And I'm going to be showing you another one in a few minutes. What we've got here is a mechanical analogy of a capacitor. We haven't introduced the capacitor yet, so don't worry about it. Just think of it as a water system at the moment. What we've got is a pump, a piston pump, and when the pump goes down, this valve opens and water flows out the outlet. So when the pump goes down, it pushes water out, this valve opens, and water comes out of the outlet. When the pump comes up, this valve opens and water is drawn out of the well into the pump. There's a problem with this type of pumping system in that we get pulses of water here. We don't get a continuous flow of water. And so the farmers who need a constant flow of water for their irrigation equipment have to do something with this to produce a constant flow. And what they do is they use a mechanical capacitor. I'm just going to bring that up on the screen for you now. There we are. And you'll find these again in supplementary downloads. You'll find these two animations. What the farmer does is he puts a sphere on top of the water line, which is fully enclosed, and open at one end where it connects to the water pipe. Can you see now that the flow of water is continuous? What is happening when the piston goes down and pushes water to the outlet, it also fills up the reservoir. When the piston is going up, the reservoir empties to fill in the no pulse period of water flow. So the pump comes down, water fills the reservoir. Now the water from the reservoir, while the pump is going up, the water from the reservoir provides water at the outlet. What the reservoir is doing is storing water for us, and that water is used during the no pump period. This is a very, very good example of how capacitors, electric capacitors, can be used to store charge, store energy, and supply energy when we don't have it. In other words, we can smooth out voltages by using a capacitor. If we've got a pulsating voltage, we can use that pulse to put energy into the capacitor, and during the no pulse period the capacitor will supply us with energy to our circuit. One of the definitions of capacitance is the ability to store charge. I don't like that definition. It's a very basic definition and it doesn't quite suit a capacitor. For example, a plastic comb can be used to store charge. A dielectric material rubbed against your hair will create a charge on it. So being able to store a charge is not something unique to a capacitor. The proper definition of capacitance is the ability to oppose changes of voltage. And if you look at this mechanical example, the reservoir capacitor on this water system is opposing the change of water flow. By having this there, we've now not got pulsating water anymore, we've got a continuous water flow. In electric circuits, we can use a capacitor to turn pulses of voltage into a continuous smooth voltage, like the water analogy here. When a capacitor is connected to direct current, suppose a battery, then the capacitor will just charge until it reaches the battery voltage, and then all circuit current will stop. Of course, we could discharge the capacitor, but that would be a slow process of charging and discharging, charging and discharging. An easier way to get current flowing at all times in a capacitive circuit is to put alternating voltage onto that circuit, and that's what we're showing here now. When the switch is closed, and it should be closed now, I'll just put a line there to close the switch. When the switch is closed, the capacitor will charge on one half cycle and discharge on the other half cycle. In other words, it will continue to charge and discharge during every cycle, which means there's going to be current flowing in the circuit at all times. No current flows through the capacitor, but there is current flowing into and out of the capacitor, and therefore the lamp will be lit all of the time. Current appears to pass through a capacitor only because the capacitor is continually charged and discharged by the AC generator. How much current flows in this circuit will depend upon the size of the capacitor and the frequency of the applied AC source. However, the current will be restricted. The current will level to an average value because when the switch is closed on the first half cycle, the capacitor will charge a little, but it may not charge the full amount, and then when the next half cycle comes along, the capacitor discharges. So the capacitor's opposition to changes in voltage also controls how much current is flowing in the circuit. So a capacitor has an opposition to current flow. It's not the same as resistance because resistance produces heat. Capacitance does not produce heat. Capacitance will draw a current but will not dissipate any power. The property of a capacitor to oppose current flow or oppose changes of current flow is called capacitive reactance, and the symbol for that is XC. Just going to have to line down, move our graphic a little bit so I can type here. Having a bit of trouble, as you can see. Let's just format that. Okay, that should work. So, repeating that again, the amount of opposition that a capacitor has to current flow is called capacitive reactance. And it's measured in ohms. And there's an equation for capacitive reactance that I'll be showing you shortly. You don't have to know the equation, but you do have to know about how changes affect the capacitive reactance. You have to know the relationship between the frequency of the generator and the capacitance of the capacitor, because that will determine the capacitive reactance. So the only things that determine it, the frequency of the generator and the capacitance of the capacitor. If a capacitor is larger, it will have less capacitive reactance. because it's able to charge more on each half cycle of AC, charge or discharge more. So a large capacitor would have this lamp dimming very brightly. A small capacitor would have it very dimly lit. If we raised the frequency of the supply, we would increase the amount of current flowing because we've reduced the capacitive reactance. I'm going to show you the formula for capacitive reactance. I don't want it to frighten you. You don't have to use it in your standard assessment, but the formula is so valuable to you because it does explain to you how capacitive reactance and therefore circuit current changes when we change the frequency of the supply and the capacitance of the capacitor. The formula for capacitive reactance in ohms is XC equals 1 over 2 pi FC, where XC is the capacitive, typo there, which I'll just fix, the capacitive reactance in ohms. You won't have to use this equation, but it's a good idea for you to know it because you can then answer questions in the exam about capacitive reactance and how the variables, frequency and capacitance, change it. Now, XC equals 1 over 2 pi FC. 1 is in the numerator, 2 pi FC is in the denominator. When you increase the size of a denominator of a fraction, you reduce the size of the fraction. And since the fraction equals XC, that means if you increase the size of either F or C, you reduce the capacitive reactance. If you decrease the size of F or C, you increase the capacitive reactance. It's an inverse proportion. XC is inversely proportional to F and C. You can't change 2 pi, that's a constant, roughly equal to 6. The only factors that affect capacitive reactance are frequency and capacitance. If anything in a denominator is made bigger, that makes the fraction smaller and therefore XC is smaller. If anything in the denominator is made smaller, then that will make XC larger, an inverse proportion. Whatever F does, XC does the opposite. If you double F, you halve XC. If F goes up, XC goes down. If the capacitance goes up, XC goes down. If the capacitance goes down, XC goes up. Whatever F and C do, XC does the opposite. Increasing F or C will decrease XC, decreasing F or C will increase XC. That's why it's a good equation to know, because you may be asked questions in your exam about how capacitive reactance varies with frequency or capacitance. And you should have a formula sheet, and this formula should be on that formula sheet for you to use in your assessment. Rightio, let's go through some of the simulated exam questions that you could get on capacitance and closely related topics. Let's have a look at the first one. Question 5.1. The unit of capacitance is the farad. Just to help you, I'll type this in. That's the unit of capacitance. The Henry is the unit of inductance. We haven't discussed them yet. We will. Inductance. And the watt, you should know already, is the unit of power. And the ohm is the unit of resistance. The answer to the question is A. The unit of capacitance is the farad, and the common subunits for capacitance are primarily the microfarad and the picofarad. You can get millifarad and you can actually get farad capacitors, but most commonly capacitances are measured as micro, meaning 1/millionth of a farad, a microfarad, and picofarads, a millionth of a farad. Question 5.2. A capacitance value of 1000 picofarads is the same as, well, here we've got to convert picofarads to microfarads. Let me get some space here so I can type a couple of things for you. Need to remember that micro, and the symbol is usually a U. It's not a U, but I don't have the Greek letter on my QWERTY keyboard, so microfarad's normally like that. Micro means 1/millionth, and pico means 1/millionth of 1,000,000. So a pico is 1,000,000 times smaller than a micro. So in order to convert pico to micro, micro equals pico divided by 1,000,000. Now the easy way to divide by 1,000,000 is to move the decimal place 6 places to the right. Since there are 6 zeros in 1,000,000, and a picofarad is a 1,000,000 times smaller than a microfarad, so we need to divide 1,000,000 into the picofarads to get the microfarads. So the decimal point is in this position right now where my cursor is clicking, and if I move the decimal place 6 places to the left, because I'm dividing by 1,000,000, 1, 2, 3, 4, then we need to put in some zeros, 5, 6. The answer is 0.001 microfarad is equivalent to 1000 picofarads. And to prove that, we could convert 0.001 microfarads to picofarads by multiplying by 1,000,000. To do that, we would start at the decimal point and move the decimal point 6 places to the right. 1, 2, 3, 4, 5, 6. And we get rid of the leading zeros. 0.001 microfarad is 1000 picofarads. So the answer is most assuredly B. Question 5.3. A capacitance of 1000 microfarads is the same as, well, micro means 1,000,000th, and 1,000,000th is 10 to the minus 6. So that's a micro, that's 10 to the minus 6 means micro. So that's 1000 microfarads. So the answer is B. 10 to the minus 3 is milli. 10 to the minus 9 is nano, and you can get capacitors in nanofarads. That's a thousandth of 1,000,000th. That's a nanofarad, and that's a pico. Uh, 10 to the minus 3 is a milli, 10 to the minus 6 is a micro, 10 to the minus 9 is a nano, 10 to the minus 12 is a pico. So that's 1,000th. That's 1,000,000th. I know I'm doing more than just answer the question here because this is useful information to you. That's 1,000,000th. And this is 1,000th of a millionth. That's nano. And pico, of course, is 1,000,000th of, I'll better put a th on it for you, of 1,000,000th. So they're in order of smallest to largest there, so it's quite a good question to help you remember those, because you may need to convert between milli and micro, micro and milli, and so on in your assessment. So make sure you do understand. If you're having trouble with exponents, these are called exponents. If you're having trouble entering them on your calculator and you want some help, I would recommend the Radio Electronic Skills Mathematics course for amateur radio. Question 5.4. A capacitance of 1 microfarad is the same as. Well, 1 microfarad is a millionth of a farad. And the options we've got are farads, millifarads, picofarads. Well, 1 microfarad is a millionth of a farad. And that looks to me like a millionth of a farad. 0.00001 is 1 millionth of a farad. So answer D is correct. Question 5.5 is similar to the last one. Again, it's asking us what is a microfarad, and a microfarad is a millionth of a farad. A thousandth of a farad would be a millifarad, little m. 1,000 farads we would never have. If we did, it would be a kilofarad. And 1,000,000 farads, we never have them. And if we did, that would be a megafarad. So the only sensible answer is A. 1 microfarad is a millionth of 1 farad. Question 5.6. A capacitance of 33 picofarads is the same as. And all of our answers are in microfarads. So what we have to do is convert picofarads to microfarads. A picofarad is a millionth of 1 millionth of a farad, and a microfarad is a millionth of a farad. Therefore, a picofarad is 1,000,000 times smaller than a farad. So to convert 33 picofarads to microfarads, we have to divide 33 by 1,000,000. The decimal point is just after the 3 there, and we need to move the decimal point to divide by 1,000,000 6 places to the right. Let's have a look at answer A, because that looks like the correct one to me. 1, 2, 3, 4, 5, 6. A capacitance of 33 picofarads is the same as 0.000033 microfarads. Question 5.7 on capacitance. A capacitance value of 0.001 microfarads is the same as picofarads. An easy one because all of the answers are in picofarads. And so we have to convert 0.001 microfarad to picofarads. To do that, we'd multiply by 1,000,000, because there are 1,000,000 picofarads in a microfarad. So we move the decimal point 6 places to the right. 1, 2, 3. That'd be 1, 4, 5, 6. That'd be 1,000. So 1 microfarad is the same as 1,000 picofarads. Do make sure you get these right, because you are immoral to get 1 or 2 conversions between microfarads and picofarads on your assessment. Question 5.8 on capacitance. The capacitance of a capacitor is increased when? Okay, we want to increase the capacitance. Would we increase the capacitance if the distance between the plates was increased? No, that would decrease the capacitance. The area of the plates is decreased. That would decrease the capacitance. the dielectric constant of the material separating the plates is decreased. That would decrease the capacitance. So I hope the last one's right. The distance between the plates is decreased. Yes. If the plates of a capacitor get closer together, the capacitance increases. If the dielectric constant is changed to one of a higher permittivity, the capacitance increases. If the area of the plates is increased, the capacitance increases. So the only correct answer we've got is D. Okay, questions 5.9 and question 5.10 are both similar questions, and I've put the equation for capacitive reactance up. Capacitive reactance XC equals 1 over 2 pi FC. And just to remind you what that's telling you, because everything is in the denominator, it's telling you that capacitive reactance is inversely proportional to everything in the denominator. That means whatever F and C do, XC does the opposite. If F increases, XC decreases. If C increases, XC decreases, and vice versa. If F or C were to decrease, XC would increase. That's the value of that equation, and it should be on your formula sheet during your assessment so you can look at it. Okay, the reactance of a capacitor does not vary with frequency. Well, that's nonsense because F is in the equation. Falls as the applied frequency falls. Okay, if F decreases, XC increases, so B is not correct. Rises as the applied frequency rises. Hang on a minute. Falls as the applied frequency rises is correct. Falls as the applied frequency rises. So F is increasing. The applied frequency rises. So F is increasing. That means XC will decrease. So the correct answer is falls as the applied frequency rises. Certainly doesn't rise as the applied frequency rises, and the last one is a nonsense one. Looking at 5.10, same sort of question. You get your answer from the equation. The capacitance, the capacitive reactance of a capacitor will be zero at all frequencies above resonance. Nonsense. Remain the same for all frequencies. That can't be so. F is in the equation. Decreases as the applied frequency rises. That's it. As this goes up, F goes up, XC will come down. If either F or C go up, XC comes down, and vice versa. Tricky the way they've worded those questions, but I hope you can see the correct answer from using the equation. Question 5.11. Which of the following is a type of electrolytic capacitor? I hope I mentioned this to you during the tutorial. There are two types of electrolytic capacitors. One is just called an electrolytic capacitor. The other is called a tantalum capacitor. Much smaller physically than an electrolytic capacitor, but still much higher capacitance compared to ceramic mica or mica capacitors. Tantalum is an electrolytic capacitor. It is polarized, so it has a positive terminal marked on it, and you must connect it the right way around, otherwise the capacitor is destroyed. Tantalum capacitors tend to be just a few microfarad, or a few tens or 100 microfarad, whereas with an electrolytic capacitor you can get many thousands, 50,000 or even 100,000 microfarads. So it's a tantalum is a small size electrolytic capacitor. Question 5.12. Three capacitors, each of 12 microfarads, are connected in series. The capacitance of this combination is. Okay, we have three capacitors of 12 microfarads in series. We divide the value of one capacitor in series by the number of capacitors there are. 3 into 12 is 4 microfarads. You would treat inductors in parallel and resistors in parallel the same way you treat capacitors in series. Question 5.13. Capacitors may be connected in parallel to increase the total capacitance. If you put two 12 microfarad capacitors in parallel, the total capacitance will be 24 microfarad. Just add them up. CT equals C1 plus C2 plus C3. You don't change the voltage rating when you put them in parallel. You certainly don't increase the capacitance. So A couldn't be the only correct answer there. 5.14. A type of capacitor suitable as an effective ripple filter in a mains operated 12 volt DC transmitter power supply is the... Well, you want a lot of capacitance for a power supply. 50,000 microfarads, 100,000 microfarads, and the only capacitor that will give you such a capacitance is a polarized capacitor. It's an electrolytic capacitor. Those big blue electrolytics that I showed you earlier on, the picture of them, they're the types of capacitor that would be used in a power supply to get rid of the ripple. The ripple is a variation in output voltage of the power supply, and remember the property of capacitance opposes change of voltage, so putting a big electrolytic capacitor there smooths out that ripple to pure DC. Capacitance opposes changes of voltage. Question 5.15. The combined capacitance of two 100 microfarad capacitors connected in series. Okay, they're in series, and the value of one of them is 100, and there are two of them in series, that will give us 50 microfarads. Pretty easy, aren't they? You might be starting to get bored with this. That's good, because it means you know it. If you're not bored with it, well, maybe you need to look at this again until you are bored with it. And of course, do the drill on capacitance to test yourself on the understanding in this section. More of the same. The capacitance between A and B in this combination is, well, what we see is two 300 microfarad capacitors in series. So the value of one is 300, and we have two of them in series, so the total capacitance is 150 microfarads. Question 5.17 is a series parallel circuit. The capacitance between A and B is... Okay, the first thing to do here is to reduce the parallel combination to a single capacitor. If we were to find out the total capacitance of 2 microfarad capacitors in parallel, we would get 10 microfarads. So we replace the 2 microfarad capacitors with a 10 microfarad capacitor. We then have two 10 microfarad capacitors in series. The value of one of those capacitors is 10, and we have two of them, so the total capacitance is 5 microfarads. Answer A is correct. Question 5.18. The capacitance between A and B is, well, we have two 1 microfarad capacitors in series. The value of 1 is 1, and we have two of them. 2 divided into 1 is 0.5 microfarad. So the correct answer is A. 519. The capacitance of this circuit. Well, the first thing to do, again, we've got a parallel combination here, and we need to replace that parallel combination with a single capacitor. There are 3 1 microfarad capacitors in parallel. That gives you a total capacitance there of 3 microfarads. So in effect, you've got 2 3 microfarad capacitors in series. So the value of one is 3, and we have, there's no correct answer there. Yes, there is. We have 3, and we have 3 capacitors. There is no correct answer. I'm going to change that. So we have 3 capacitors. No, sorry, that was correct. I shouldn't have changed that. Should have left it as it was. This resolves to 3 microfarads. We have 3 microfarads in series with 3 microfarads. We have 2 of them, so 3 microfarads divided by 2 equals 1.5 microfarads. So the correct answer in this one is B, 1.5 microfarads. Just remember, with series parallel circuits, reduce the parallel circuits to a single capacitor and redraw it if you like. If I redrew this, I would be drawing 2 3 microfarad capacitors in series. Gives you 1.5 microfarads. 520, the capacitance between A and B. Well, we have 3 12 microfarad capacitors in series. The value of one of them is 12. The number we have is 3, and that equals 4 microfarads. Not too hard, is it? And you'll be getting lots and lots of practice doing these, and you'll also get lots of practice with the drill questions on similar questions like this. This looks like it might be a duplicate question. Anyway, it doesn't matter, won't hurt us. The capacitance between A and B, you've got 3 1 microfarad capacitors. That reduces to a single capacitance of 3 microfarads. You have 3 microfarads in series with 3 microfarads, so the value of one capacitor is 3. The number you have is 2. 2 divided into 3 is 1.5 microfarad. So the correct answer is C. 522, the capacitance between A and B, well, all you've got in the diagram is 2 0.5 microfarad capacitors in parallel. You simply add them up in parallel, and that gives you a total capacitance of 1 microfarad. Getting a little repetitious, isn't it? The capacitance between A and B, excuse me, we have 2 600 microfarad capacitors, so the value of one is 600. The number we have is 2, and that gives us 300 microfarads. So the correct answer is B. (524) The capacitance between A and B is, again, we've just got them in parallel. We've got capacitors in parallel, so we simply add them up. Very easy when capacitors are in parallel. Add them up. 3 15s, 45. Answer is 45 microfarads. Question 525. The combined capacitance of 2 300 microfarad capacitors in series is, well, we have the value of one is 300, and we have 2 of them, and so the total capacitance is 150 microfarads. The correct answer is A. Question 526. Capacitors may be connected in series. Well, you do 2 things if you connect capacitors in series. You decrease the total capacitance, but you increase the voltage rating. If you had 3 capacitors rated at 100 volts and you put them in series, the total voltage rating of that series combination is 300 volts. But let's see what the answer is. Capacitors connected in series increase the total capacitance? No way. Decrease the total reactance? No way. Decrease the voltage rating? No way. Decrease the total capacitance. When capacitors are placed in series, the total capacitance is smaller than the smallest capacitor in the series circuit. Question 527. Capacitors may be connected in series too, similar to the last one. Well, in a series connection would certainly not increase the total capacitance, would not decrease the total reactance, decrease the voltage rating, increase the total voltage rating. If we have two 10 microfarad 10 volt capacitors in series, we would end up with 5 microfarad and 20 volts. So connecting them in series reduces the capacitance, but it increases the voltage rating. And sometimes we need to increase the voltage rating because we're connecting capacitors to a very high voltage power supply. Well, that completes tutorial number 8 on capacitance. And that's about all you really do need to know about capacitance for your standard amateur radio assessment. However, I have placed in the document folder of your CD or DVD 2 files called BE3 and BE4. They're PDF files, BE3.pdf and BE4.pdf. That's reading material on capacitance. That reading material is thorough and it goes much further than you need to know for your standard assessment, but it's there in case you want to look at it. I would suggest you don't get too bogged down in reading that material because there's more information there than you need to know, and you really want to focus on where this course is taking, and that is to a quick exam result. So if you start doing too much reading, you can bog yourself down and make the course too difficult. But if you want to read more about capacitance, have a look in the document folder of your DVD and you'll find 2 files there. Give them a read over. Don't worry about them too much. It'll just give you a little bit more information about capacitance and capacitive reactants. BE4 and BE5.pdf. Thanks for listening. I hope that was useful to you, and I'll see you again in the next tutorial. Cheers for now.